Great. So now we have a catalog, a growing catalog of stars to which we know the distance. We have pulled those stars, at least some of the stars nearby, down off of the celestial sphere. We know the distance to them. They live in our three-dimensional universe. What does that tell us about them? Well, it tells us a lot. Let's start by seeing what we can tell about a star just by looking at it. That's all we can do with stars, but assuming that someone tells us, because we measured carefully the distance to it. Well, one thing we can do is we can do a photometric measurement. We can measure the brightness of a star. Literally, you aim a telescope with a known aperture area at the star and measure the rate at which the telescope gets energy from the star. You correct for dark sky. There's a process. It's not that difficult. But if we know the brightness, then we can remind ourselves that brightness is related to luminosity of the star by this expression. Brightness is luminosity divided by 4 pi d squared. If we know the brightness because we measured it, we know the distance because we measured it, we can extract an expression by solving this for the luminosity. So we know the actual luminosity of a star. Now we can tell you, is this some very huge, very luminous star or some very tiny star? This is one form to write the equation. A more convenient form in which to write it is to scale it to something known. In other words, this same equation holds for any star. In particular, it holds for the sun. And the advantage of writing it in this way is now, what this suggests is if I divide the left-hand sides and set that equal to the ratio of the right-hand sides, first of all, the 4 pi's and whatever constants are sitting around cancel, but more usefully, I now get a product of dimensionless quantities. I get an expression that says that this divided by that is this divided by that, or this expression here, where I have plugged in that the value of the distance of the sun from Earth is 1 astronomical unit, and the sun's brightness is the solar constant. So we have a dimensionless object, the luminosity of the star in units of solar luminosity, written as the product of two others. Whenever possible, we'll write it that way. Okay, now we know the luminosity of a star. What else can I get just by looking at it? Well, if I'm careful, I can measure the star's color. And the star's color, as we know, gives us information about its temperature. If I find the maximum of its black body spectrum, I can get an estimate from the temperature from Wien's law. So there's Wien's law. It relates the surface temperature of a star to the wavelength at which it emits its maximum emission. This is written in Kelvin. And now, if I know the temperature and I know the luminosity, I can remind myself that I had yet another expression for the luminosity of any star. L was equal to the sigma t to the fourth given by Stefan Boltzmann law for the rate at which each square meter of the star surface radiates, times the surface area of the star, which in terms of the star's radius is given by 4 pi r squared, where r is the star's radius. And now, if I know t and I know L, I can extract an expression for r. I find that r squared is L over 4 pi sigma t to the fourth, or if I just want r, I simply take the square root of both sides. And I can rewrite that as the square root of L over 4 pi sigma times the square root of 1 over t to the fourth is t to the minus 2, 1 over t squared. And in this form, again, I can compare to the sun by dividing this expression for the star by the same expression for the sun. The radius of the sun is luminosity of the sun, square root divided by 4 pi sigma, 1 over the temperature, solar temperature squared. And this gives me another one of those nice scaling expressions. But the bottom line is, if I know the temperature and the luminosity, for which I needed observations in the distance, I can get the radius of a star. Now, some stars, a few tens, have actually been imaged, and this is a recent development. There's a few tens of stars for which the radius has actually been measured empirically, optically, by imaging them and measuring the angular distance between the left and the right side of the star. This is a new result, but most stars, when we say we know their radius, we know it from this. This is brilliant. We can learn a lot from a star, about a star, if we know its distance. The problematic measure here is the temperature. Remember, we said the black body spectrum is very broad. If you're on a very broad mountain, identifying exactly where the summit is can be a problem. In the same way, finding the precise maximum of a very broad black body spectrum is a difficult and imprecise task. We want a better thermometer, since measuring the stellar temperature is so important. And it turns out that we have a better thermometer. It's also less subject to distortion. For example, if there is a cloud of gas or dust between us and the star, we know that will preferentially scatter blue light. A star viewed through dust or gas will appear redder than it is, and that might mislead us into thinking it is cooler than it is in fact. If you looked at the sun at sunset and tried to devise its temperature from its color, or even in the middle of the day, you would conclude that it's yellow rather than green. Now, something that is not distorted by intervening media is the star's absorption line spectrum, so we can look and understand something about the chemical composition of the star's atmosphere. This was known, and there was a big ongoing project late 19th, early 20th century into the 20s to classify the forms that stellar absorption spectra take. It was clear that there was a lot of information there, but it wasn't clear until the 20s exactly what it is that we are classifying when we classify stellar spectra. We now understand the classification. Here is a sort of compilation of representative stellar spectra arranged in order of what is called spectral type, and spectral type runs from O through B, A, F, G, K, and M, and within each category there are 10 subdivisions. So B0 is on one end, and then it goes all the way up to B10, and A0 up to A10, and so on. And if you notice, there are sort of properties, there are spectral lines that are very prominent, say, in this region between the B's and the A's, but almost absent in the O-type stars and then disappear again in the F stars. This, for example, are the spectral lines of hydrogen. These are Balmer lines of hydrogen. And the interpretation that is understood in the 20s is that this organization, and the reason B comes before A is because there was previously another organizing principle, and this was understood later. This organization is in direction of decreasing temperature. So O stars are the hottest stars and M stars the coolest stars. And for example, if you look at the hydrogen in the stellar atmosphere, then O stars are so hot that the hydrogen is essentially all ionized. And in B stars, much of the hydrogen is ionized. An ionized hydrogen atom is just a free proton and an electron. There is no absorption line spectrum for a free proton. So hydrogen lines are almost completely absent from the spectrum of O and are very weak in the spectrum of B-type stars. In the cooler Bs and in the A-type stars, hydrogen lines are very prominent because hydrogen is now atomic. The ambient, the light that the star is emitting is at high frequency, so and the temperature is high enough that these hydrogen atoms get excited to their excited state, and we observe this line, which is associated to a hydrogen atom in its first excited state. The hydrogen atom ground state, excitations of the hydrogen atom from the ground state are ultraviolet, and they don't appear in the visible light spectrum. And indeed, as we proceed in lowering temperature, once we go from A to F-type stars, the hydrogen lines weaken and eventually disappear because hydrogen in the cooler atmosphere of F-type stars is in the ground state, and if it absorbs anything, it absorbs ultraviolet light. Very few of the atoms are in the first excited state where they can absorb visible light photons, so hydrogen lines disappear. What starts to appear is the spectral lines over here of ionized metals, heavier elements. You see these forests with many, 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 many lines in them. And these are characteristic of more complex atom. So these are the spectral lines of ionized metals. And in cooler stars yet, in the cooler Gs and the Ks, we find the spectrum of neutral metals. So now the temperature is cool enough that heavier atoms do not become ionized. And in the M-type stars, in the cooler M-type stars, we actually find these bands, these way broadened bands of absorption. This corresponds to the existence of molecules with internal degrees of freedom, and so they can absorb light at various wavelengths. And so this progression is a progression in temperature, and once you understand that, we know that we can use this as a precise thermometer. Here is the current list of spectral types. They are listed according to the color, though color perception of stars is very subjective. Here are the temperatures. Note that the temperatures at stellar surfaces range from as hot as 50 or 60,000 Kelvin in hot O-type stars to 2,000 or 3,000 Kelvin on the very cool dark red M-type stars. And these are the sort of description of the spectral features that characterize them. This is their prevalence, and I should be careful. This is our understanding of the prevalence of this type of star among all stars. I'll explain why this needs some qualification, and note that it is precisely increasing as you go to cooler stars. So the coolest M-type stars form 3/4 of all known stars, whereas the O-type stars form a tiny, tiny fraction. And the cooler the star is, the more likely it is to appear. And here are some examples of stars of each spectral type. And so dark red Betelgeuse and orange Arcturus and Aldebaran are examples that we're familiar with. The Sun is a G-type star, in fact, G2 within the internal classification of G-type stars, and Sirius and Vega are A-type stars, and so on. The bright stars of Orion's belt are O-type stars. Some of these stars are listed here in not in black type, and in the next clip we'll understand. What we now have is a collection of data about stars. We now have a huge population of stars about which we know their luminosity, their radius, their temperature, and we can start trying to arrange this data as a sociologist would to do a population study and try to draw conclusions. We'll figure out how to organize it in the next clip.